In this presentation, we'll talk about prime numbers and how to find prime numbers using a computer. In a future presentation, we'll talk about the usefulness of these prime numbers. Prime numbers are a special kind of number. They are numbers that you cannot divide by any other number except 1 or the original number itself, and get a whole number as a result. For example, 7 is a prime number because you cannot divide 7 by any other whole number and get a whole number as a result. If you divide it by 2, you'll get 3.5 as the result. That's not a whole number. You could divide it by 1 and get 7 as the result, and you could divide it by 7 and get 1 as the result, but those are your only options. The next prime is 11. You can divide 11 by 1 and get 11 as the result. And you could divide 11 by 11 and get 1 as the result. But once again, those are your only options. Some other numbers that are easy to see as primes are 13, 17, 19, and many more. As you may have noticed, no even numbers after 2 are prime because you can divide them all by 2 and get a whole number. For example, 24 is not prime because 24 divided by 2 is 12. We call it a composite number, which is the opposite of prime. We're going to ignore 0 and 1 right now because they have their own special rules. So, since even numbers are not prime, when we try to come up with a list of prime numbers, that takes half of all the numbers off the table right away. So multiples of 2 like 4, 6, 8, and 10, and so on, cannot be prime. Similarly, multiples of 3 like 6, 9, 12, 15, and so on, can also not be primes. We can keep doing this to get a sense of which numbers cannot be primes. For example, multiples of 5 like 10, 15, and 20, or multiples of 7 like 14, 21, and 28. You get the idea. None of those multiples can be prime numbers. Now it might seem that after a certain point, all of these multiples would leave no numbers behind to be prime. But here's the thing. The ancient Greek mathematician Euclid proved that there are an infinite number of primes. The list just never ends. The largest known prime number is a super long number with almost 25 million digits, and they're still calculating larger ones. The next interesting thing about primes is that all numbers can be produced by multiplying prime numbers together. That same Greek mathematician Euclid proved this as well. It is called the fundamental theorem of arithmetic. Every integer greater than 1 is either a prime number itself or a number that can be represented as the product of prime numbers. For example, take 12. It can be expressed as 2 times 2 times 3. Remember that 2 and 3 are primes. What we've done here is called factorization. We take 12 and figure out what primes we need to multiply together to get 12. Factorization. Another example, a little bit harder, is 155. It's 5 times 31. With a small number like 12, you could just think about it for a minute and come up with its factorization, which is 2 times 2 times 3. That's a pretty small number. But what about a large number, like 2,244,354? It's really hard to factorize that number. It's very hard to find out that 2 times 3 times 7 times 53,437, which is a prime, equals this number. And imagine trying to find the prime factors of a number 50 digits long. That's a tough problem. Even though the best mathematicians have worked on this problem for hundreds of years, there's just doesn't seem to be any way to factorize large numbers efficiently. Prime numbers are really important for things like cryptography. What is cryptography, you might ask? Cryptography refers to scrambling messages to keep them secret. When you send an encrypted message, only someone with a special key can unscramble the message and read it. But we'll talk about cryptography in another video. Since prime numbers are so important in math, I decided to think of a few ways to generate prime numbers using a computer. I thought of 3 ways to generate prime numbers, and then I tried a method from a Greek mathematician, Eratosthenes. Each of these 4 methods will give you a list of primes up to a certain number that you have chosen. For example, all the primes up to 1 million. Method 1. Divide by all smaller numbers. The way this method works is that you take a number and you divide it by all the whole numbers smaller than it down to the number 2. And what we want to see is if the answer of any of those divisions is a whole number. For example, let's take the number 10. Divided by 9. 10 divided by 9 is at 1 point something. It's not a whole number. Now try 10 divided by 8. That's 1 1/4. Once again, not a whole number. Now try 10 divided by 7. Also not a whole number. But when you get to 10 divided by 5, the answer is 2, which is a whole number. So 10 is not a prime number. Take another example. 13 divided by 12, and you get 1 point something, not a whole number. Same goes for all the numbers under it, other than 1, of course. So 13 is a prime number. That seems pretty simple. Of course, this takes a lot of time to do all of those calculations. Of course, computers can do these calculations quickly. But even for computers, doing these calculations for all the numbers up to, say, 1 million, it will take some time. In fact, let's say that it takes a second for each of those calculations. At that rate, it would be almost 16,000 years to do all of those calculations up to 1 million. If we did that, we'd have all the prime numbers up to 1 million, but that's a lot of time. Of course, computers are faster than that. So I wrote a computer program to do this, and in actuality, it took only about 1.2 hours to find all the prime numbers up to 1 million. By the way, there are about 80,000 of them. But 1.2 hours is still a very long time for a modern computer, meaning that this method is very inefficient. I knew there must be a better system, so I came up with another method. Method 2. Divide by half of the smaller numbers. This method is pretty much the same as the first one, but we start dividing at the number which is half of the number we're checking. So, if we're trying 10 to see whether it's prime, we start by dividing it by 5, then 4, then 3, etc. The reason we could skip numbers over half is that if you divide a number by another number that is over half its size, it is impossible to get a whole number as the answer. For example, 100 divided by 99 is not a whole number. In that case, we could start our calculations at 50. When I wrote the program for this technique, it took just about half of the time. It took, as expected, 33 minutes. So that's more efficient. But I knew that I could do better than this. 33 minutes is still too long. Method 3. Divide by primes. Remember that I mentioned the fundamental theorem of arithmetic, that every number is either prime number or a multiple of prime numbers. So if we're doing something like the previous 2 methods, we don't actually need to divide by every smaller number to see if we get a whole number answer. We have a giant advantage. For the number we're testing, we only need to divide by all of the prime numbers under it. And there are a lot fewer prime numbers than normal numbers. So here's an example. Let's take 16. You might think that we need to test it by dividing it by 8, 7, 6, 5, etc. When in fact, we only need to test it by dividing it by 2, 3, 5, 7, which are all of the prime numbers under half of the value 16. Now, this might not seem like a big advantage, but when we're testing a number like 1 million, there are a lot fewer primes than half of a million, which is 500,000. In fact, there are only about 70,000 primes under a million, and we only need to check the primes under 500,000. And that is only 41,538 prime numbers. That's a lot fewer calculations than 500,000. So this is an amazing shortcut. This method took only about 3 minutes for my computer to calculate for up to 1 million. Method 4. Sieve of Eratosthenes. The ancient Greek mathematician Eratosthenes came up with a method to create a list of prime numbers in a certain range. This method is to start with a list of all the numbers in your range. Then you mark out all the multiples of 2 in that range. So, other than 2, you mark out 4, 6, 8, 10, etc. Then you mark out all the multiples of 3 in that range, other than 3. So you mark out 6, 9, 12, etc. Then you skip 4 because it has already been marked out. And you do 5. So, you see how we got a shortcut there? We didn't need to calculate all of the multiples of 4, because all of the multiples of 4 are multiples of 2. Same for 9. We don't have to calculate and eliminate the multiples of 9, because 9 is a multiple of 3. So any of 8's multiples have already been eliminated from the list when we did 3. That means that we don't need to do as much work, which means that we are being more efficient. We continue marking out multiples for all of the numbers in the range. When you get rid of all of the multiples, you're left with all of the primes in the range. All of the numbers that you haven't marked out are primes. That sounds like a lot of calculations, but remember the shortcut? There are more and more shortcuts as we go through the list, meaning that we don't actually have to do as many calculations. I wrote a program to do this, and surprisingly, it took longer than I expected. It took 4 hours for my computer to do the calculations using this method. This is a good method for humans because you're able to picture it well, and it's very visual. For me as a human being, it seems easy to look at a 10 by 10 list and mark out all of the multiples of 2, 3, 5, 7, etc. And I could even look at a giant table, 100 by 100, and still get the picture. That would be 10,000. You could imagine marking out all the multiples of 2, and then 3, etc. It's really visual, and human beings love to see things visually. But for a computer to do this, it needs to run through the list of 1 million numbers many times, over and over and over. And it turns out that that takes a long time. So, it's inefficient. Primality tests. Up until now, we've been talking about ways to create a list of all the prime numbers in a range of numbers. But what if you'd like to test a gigantic number to see whether it's a prime? A number so big that you don't have a list of all the primes leading up to it. If it's an easy number like 1009, it would be trivial to tell your computer to generate all the prime numbers up to 1009, and then you would know that 1009 is indeed prime. But what if you're checking the largest prime number currently known? The one we mentioned earlier, that was 25 million digits long. You can't just tell your computer to generate all the prime numbers up to that enormous number, because it would take way too long. So mathematicians have come up with a different approach. Rather than generating all of the numbers up to a number that you want to test, they created something called a primality test, which is a way to check a number to see if it's prime number or a composite number, even if you don't have all the prime numbers leading up to it. One of the most famous primality tests is called the Miller-Rabin primality test, which was developed by Gary Miller and Michael Rabin in the late 1970s. The details of this amazing test have been published openly, and here's how it works. Here's an example using an easy number. We're going to test whether 13 is a prime number. Obviously it is, but let's test it. So here's how the process works. Don't worry if you don't perfectly follow this explanation. It's a big deal in the math world, and it isn't at all trivial. We've chosen the number 13 to test, so let's put the number 13 on a shelf. We start by taking one less than the 13 we just put on a shelf, namely 12. Then we follow these 3 steps. Step 1. In step 1, our challenge is to choose 2 numbers that you can put into this formula. The formula is d times 2 to the power of r. And we want to make that formula equal 12. The catch is that d in our formula has to be an odd number. So we begin with an easy trick. Here's the trick. If someone asks you, give me x and y so that x times y equals 12, you could just simply say that x is 1 and y is 12, so 1 times 12 is clearly 12. Simple. 1 times any other number is that same number. So we're going to use this trick in our formula. We're going to make sure that 2 to the power of r is 1, so that d can simply be 12. To do that, we choose r equals 0, so that 2 to the power of r is 1. If we make d equal 12, then our formula will give 12. The problem is that we need d to be an odd number, and right now it's 12. So our next step is to chop d in half, in other words, divided by 2, and then increase r by 1. When we divide d by 2 increase r by 1, we're essentially dividing it by 2 and then multiplying it by 2. So that keeps things even. And we're still getting 12 as our answer. Still, our d is not odd, so we're not done. We have to do that again. Divide d by 2 and add 1 to r. So now we have d equals 3 and r equals 2. d times 2 to the power of r will give us 3 times 4, which is 12. And voila! Now d is odd and our formula works. Next step. Step 2. Now, step 2 might seem weird because it is going to use a randomly chosen number. This takes us into probabilistic math, meaning that whatever answer we will get will have a small chance of being wrong, but we'll deal with that later. So, here's step 2. We choose a number between 2 and 11, any number does the trick, and we call it a. Let's choose 7, so a equals 7. We take the d that we got in step 1, and we calculate a to the power of d. So for us, a to the power of d would be 7 to the power of 3. The answer is 343. So 7 to the power of 3 equals 343. Then we take that number, 343, and divide it by the number we're checking, our original number, which is 13, which you'll remember we put on a shelf at the beginning for safekeeping. Here's the weird part. We don't care what the answer to 343 divided by 13 is. We only care about the remainder of that division. This might seem crazy, because usually when we do arithmetic, we care about the answer, not just the remainder of some uneven division. But we're now stepping into an area of math that deals with remainders. The math word for remainder is modulus. So this area of math is called modular math. Let's go back to our problem. 343 divided by 13. The answer is 26 with a remainder of 5. Remember, all we care about is the remainder of 5. Isn't that strange? At this point, the test tells us that if the remainder is 1, or 1 less than the number we put on our shelf, in our case 13, so if the remainder is 1 or 12, that means that the number we're testing, which is 13, is most likely prime. Remember, we're in probabilistic math, which means there's a small chance of making a mistake. Step 3. In the next step, similarly complicated, we take that remainder answer from the previous step, which was called x, and in our case was 5, and we square the x and then divide it by our original number from our shelf, 13. And again, we only take the remainder. So remember, 5 times 5, because we're squaring it, divided by 13. In our case, that's 25 divided by 13, which has a remainder of 12. 25 divided by 13 equals 1 with a remainder of 12. Now, we call x 12 and simply ask 2 questions at this point. If x is 1, then the number we're testing is not prime. If x is 1 less than the number we're testing, like 12 in our case, then the number we're testing, which is 13, is probably prime. In our example, this is exactly what we get. X equals 12, which is 1 less than the number we're testing. So the Miller-Rabin test says here that 13 is probably prime. Now, step 4. Lastly, we run steps 2 and 3 many times over. Remember that in step 2, we chose an arbitrary random number in a certain range. Well, now, when we run these steps over and over each time, we use a different random number. As we do this, the test refines its answer to become very, very accurate. After you run it a few dozen times, the Miller-Rabin process tells us, in the end, whether our number is prime. In our case, 13. The answer is, of course, yes, it is prime. So, what we've seen in this method is that it uses some unusual techniques. Arithmetic of remainders, modular math, random numbers, and repeating a probabilistic process numerous times to achieve higher accuracy. I programmed this Miller-Rabin primality test into a computer based on the published algorithm that I just explained. I tested a number that was 20 digits long to see if it was prime. 20 digits numbers are very big numbers. In our case, 48 quintillion. And it took my computer only a fraction of a second to get that answer. So, in summary, we looked at 3 methods to generate a list of prime numbers, and I programmed the famous Safavier-Tostany's method. And I tried out the also famous Miller-Rabin primality test. And we got very interesting results. So, in another presentation, we'll talk about the usefulness of these prime numbers in cryptography.